Hello, welcome to CSC 351, the Introduction to Data Science. Today's topic is on gradient descent algorithm and also an extension to this algorithm called a stochastic gradient descent algorithm. So far in topic of classification, we said that we need to find a function that can predict the desired label for an input feature so that this label be as close as possible to the true or actual label. So we usually decide on what kind of function we wanted to use, but this function has some parameters. Therefore, we need to estimate the parameters of this function in order to fulfill a requirement or an objective function. So this objective function is called a loss function. Gradient descent algorithm is one of the most popular techniques that is used to find the parameters of an objective function. But before we talk in detail about the gradient descent algorithm, we need to have a review and revisit derivative and partial derivative, which you have learned in high school. So consider a function f, where this function for an input variable x give us the output y. So when you take the derivative of this function with respect to variable x, what is the meaning of this derivative? So that's helps us to understand gradient descent algorithm. And in fact, the gradient descent algorithm is simply based on the concept of derivative. So for now, we consider a function that only has one variable. So you also need to know the concept of a slope. What is the slope of a curve? Because the derivative of a function at some point is closely related to slope of that function. So let's consider the function for the input value x1. This function generates y1. And then for the another value x2, this function generates y2. Okay, and then also consider that x1 and x2 are close to each other. So now I wanted to give you a graphical representation of what we are, so what's the definition of derivative. So then I can define delta as a slope of this line, and then call it as so y2 minus y1 divided by x2 minus x1. In other words, if I have a graph like this, in Cartesian plane, let's say we have this graph, and then consider this point is x1 and this point is x2, and this is on the y-axis, this is y1, and this is y2, right? So then the value, the delta value, basically in here indicate the slope of this slope of this line, which is show it from. Let's use another color. Let's use green. From here to here is give me the slope of this line. Okay. So we also note that in here, because x2 is greater than x1 and also y2 is greater than y1, we know that the delta is positive. Delta is positive. So in other words, the slope going from x1 to x2 is positive. So what's now the definition of derivative? The definition of derivative is when the value of this point is moving toward x2 is moving toward x1, and in the limit the distance between x1 and x2 approaches to 0. So that's delta is converted to derivative. So it's basically we say this is derivative of f of x with respect to d of x is simply approximately is equal to y2 minus y1 divided by x2 minus x1 when x2 approaches x1, right? Approaches x1. So therefore, the derivatives gives us the slope and also the direction. Either if compute the derivative at this point, the function increasing or decreasing, right? So that's the two important pieces of information we can get from derivative. So derivative basically gives us a slope. The magnitude of derivative give us this is a high slope, low slope, and then also the sign of derivative tells us if the function at this point is decreasing or increasing. So that's two important point. So these two concepts is used in gradient descent algorithm. So in gradient descent algorithm, we have a function which has a parameter, and then we wanted to find the variable that minimize this function or maximize this function. So simply we know from math, if you wanted to find a mean or max of a function, simply we can take the derivative of that function and then set the derivative to 0, and then the value that makes the derivative 0, it's the mean or max of that function. But when it comes to optimization and also classification, the function we are dealing with is not, we cannot take the derivative of this function, or derivative is so complex, or derivative doesn't have a closed form. Therefore, we cannot use that trick that we take a derivative of function, set the derivative to 0, solve it for the independent variable, and then the answer is the mean or max. And then these are the parameters of that function or parameters of our classifier. But we cannot take the derivative. But imagine that now we have an objective function. This objective function or loss function, we can't take the derivative of this objective function. And this objective function tells us if we take the derivative at the point and then we can find if this function is, the slope at this function is low or high, or and then if this function at this point is increasing or decreasing. So therefore, this is the basic idea behind gradient descent algorithm. So what we do, we basically take the derivative and then compute the value of derivative for some point. If the derivative is positive, that means we need to move in another direction in order to find the minimum. Let's say we do this in here. Let's say I start from this point, a random point, take the derivative and see the derivative, slope of derivative is positive. That means the function in this direction is increasing. Note that I wanted to find the minimum of this function. Therefore, I know if I take this path, then the value of this function decreases. Therefore, I can say the minimum is this point, but moving to other direction of slope. So then I can move a little bit in here and then compute the derivative at this point, and then if I see that the slope is still positive, I move in an opposite direction, and then I take the more step until I get at some point that the derivative is 0. So when a derivative is 0 for that point, that's an indication at this point the slope is 0. So this point is correspond to a mean or max. So also you should know when the derivative is 0, at the point, that point correspond to a mean or max. However, it's also extremely important when you're dealing with the taking derivative of an objective function. This function, they don't have only one global minimum or global maximum. This function might have several global minimum or maximum. Let's take a look at this curve. So let's say the objective function looks like this. Okay, so this function, which is an objective function, how many minimum this function has? So basically this is 1 minimum, 2 minimums, 3 minimums, 4 minimums. How many maximum? There is 1 maximum here, 1 maximum here, 1 in here, 1 in here. See? So these are called, these means are called local minimum. Local minimum. These are local minimum, and these means are basically global. This mean is global minimum. And also we have local maximum and global maximum. So for this case, this point is a global maximum and these points are local maximum, right? So now when you're dealing with an objective or loss function, you are dealing with, it's very complicated. And also note that this is not only, the function is not only depending on one variable, one parameter. There are tons of parameters. For real applications, right, neural networks and loss function depends on maybe million of parameters. So then you can imagine how the objective function looks like. So complicated, and in this complicated function we are looking for a global mean or max. But unfortunately, none of the optimization algorithms guarantee that you can find a local minimum. A global minimum. They're always finding a local minimum, but there are some tricks that you can apply that make sure that you are in a global minimum or you're in a good local minimum. So these are important points when you are dealing with an optimizer. You should take it into account. So for now, what we know, we know that when we take the derivative of the function, basically compute the slope of at that point. If this slope is increasing, then we know if we take steps opposite of that derivative, then we go toward the local minimum. And then also the sign of the derivative tells us is function increasing or decreasing, as I showed in this very simple example. This, and also the next thing about the derivative is partial derivative. As I said, the function we are dealing with, they're a function that they're having multiple parameters. So we are dealing with function like f of x1, f of x2, f of xp, where these x's are input features, or input parameters, these are input parameters. And then we need to find each of these parameters. That means we need to take the derivative with respect to each of these parameters. So then we define the partial derivative. So partial derivative of y with respect to xi. That means when we wanted to take the derivative, we consider all parameters as a constant, and then we only consider xi, and then take the derivative with respect to xi. Okay, so that's how we take the derivative. A simple example, let's say if y is equal to x1 plus x1 squared x2, then the partial derivative of y with respect to x1 is equal to derivative of the first point, which is 1, plus the derivative of x1 squared, which is 2x1 x2. You see that x2 in here is considered as a constant. And then we can also take the partial derivative of this function with respect to x2, which is basically x1 squared. Okay, so these are two preliminary concept and also tools we need in order to proceed and understand the gradient descent algorithm. Okay, so now we are ready to define and formally approach the gradient descent algorithm. So consider here we define a loss function. As I said, for all classification problems, we define a loss function, and and then objective is to minimize this loss function with respect to some parameters, and these parameters are parameters of classifier. So how to form the loss function, it's highly depends on your application, but in today's state of the art classifiers, they are based on the mean square error criteria or cross entropy. So we'll consider both in here. So let's start. We have n samples from a distribution and from a classification task, and then in this classification task we have an input vector xj, so this is the j sample, and when you put this input sample, the classifier will try the label for this sample. This label, for instance, you can put an image, and then the classifier tells you this is a picture of a cat or some other things, or you can put a patient information as xi, which is a vector, and then you have a binary classifier saying this patient suffers from a particular type of disease or cancer or not. And there are tons of millions of other examples for classifier. So the goal is, as I said, for the classifier is to design a function which input to this function is this vector, and this function has some parameters. We call them A. It's a vector, and this vector represents all parameters in this function. So A is usually called the parameter vector, and F is a known function. Note that when we are designing classifier, we first make an assumption. We say, okay, the function that map the input to output should have this form. So we know that this is a linear function, this is a nonlinear function. We know the form of this function, but we don't know the parameters of this function. We don't know the parameters of this function. For instance, when we talk about the logistic regression classifier, we know this is a Logitech function, but we don't know the parameters of that Logitech function. This is important to note that f is always known, but the parameters of f are what we need to compute. So then what we're looking for, so we wanted to find the parameters of this function or parameter vector such that the f is as close as possible to y. So for all samples. Then we need to create an objective function or a cost function. And then we apply an optimization algorithm to this cost function. So in here, I showed the mean square error loss function or cost function, in which that we wanted that for each sample, when we put the input, the output of this function be as close as possible to the actual label. So if they are equal, that's 0, then the loss function is 0 or the cost function is 0. Therefore, we basically consider the difference between the input and output, and we want it to be the difference be insensitive to positive, negative. Therefore, we take the derivative, and then we want it for all samples. When you put the input, you get the desired output. Therefore, we sum for all samples, and then we also normalize it by number of samples to don't let the mean square error objective function grow unboundedly. So at the end, what is important in here, we have a loss function, we call it J. In these lectures, I use the notation J. And this function, this objective function, is a function of the parameter vector. So note that if you look at the right-hand side of this equation, so yj, which is the j sample output in training phase, we have it. F is known, as I said, the formal function we know. X superscript j is also known. This is the input. The only thing is not known in here is parameter. Therefore, the loss function is a function of parameter. So what is the goal? Now the goal is to find the vector, the parameters that minimize this objective function, which basically means if this function is minimized, that means the output of this classifier is as close as possible to the actual output. Also note that you can design your own cost function. But this cost function is one of the most popular one, along with what is called the cross entropy. And cross entropy, when the output of your function is a probability, then we use the cross entropy. We will get to the cross entropy shortly in next video lecture. So now what we wanted to do, we wanted to basically find the vector A that minimizes function, and this vector is the estimated parameters, which now guarantee the function f outputs some labels which are as close as possible to the actual labels. So now the classification problem during the training phase is to find these parameters, or to first have a loss function and then find the value of A that minimizes that function. This is all about the training phase during the classification. So now the entire discussion is now is focused on how to find the minimum of the loss function. So then how to find the minimum loss function? We use the gradient descent algorithm in here, but there might be, this is an optimization technique, optimization method. or we call also the gradient descent algorithm as an optimizer. We need to apply an optimizer to find the minimum for this loss function. So why we are using gradient descent algorithm? This is very simple one, very effective one, and also very fast. It's a very fast algorithm. And also neural networks, which I said they are the state-of-the-art classifier for big data. They are all working based on the gradient descent algorithm during their training in order to find the parameters. Of course, there are some extension and modification to gradient descent algorithm, but the basic idea is the same as the gradient descent algorithm. So, gradient descent algorithm is an iterative method in order to find the local minimum for the loss function. So we have a loss function, and this loss function, note that this is a function of a vector, or this is a function with multivariate inputs, not only one input. Okay. Okay. So in here we formally define the gradient descent algorithm. Gradient descent algorithm is an iterative method. We basically start by a random guess for the parameter vector, and then there is no guarantee this random guess is the correspond to the point that minimizes the loss function. But what we do an iterative steps in which we compute the derivative of the loss function. We compute the derivative of the loss function for each parameter. So we know that the A is a vector of the parameters. Parameter 1, parameter 2, let's go all the way parameter k, and then until, let's say if you have k parameter, so these values are scalar. Okay, so we need to compute find all these parameters. So for each, and then we call this number p, number of parameters. So for each of these parameters, we take the derivative, the partial derivative of the objective function with respect to each of these parameters. And then we basically start by initial point, and then we move toward the negative of the slope at that point, at the random points. So if we start from, let's say, this is the j of a, we start by a random point in here, and then we take the derivative, and then we move toward the negative of the slope, and then we iteratively compute the derivative until we get to the point that the derivative doesn't change. So when we stop, in the gradient descent algorithm, there are two criteria that is requirement for stopping. Ideally, we want a derivative be 0. So when the derivative is 0, that means we are now in a local minimum, because there's no slope. When there's no slope, then we are in the local minimum. But usually when you're dealing with the very complex function, it's not achieved. So therefore we define that when the difference between the parameters at current state and previous one is smaller than a threshold, and then this threshold is small value, then we stop the gradient descent, or we set a maximum number of iteration. Let's say do 1,000 iteration, and then hopefully within the 1,000 iteration we arrive at the local minimum. So you can set either of these thresholds. Usually we use this threshold. That means when the update for parameters doesn't change and this is smaller than a number, like say if it's smaller 10 to the power of minus 5, then we stop the gradient descent algorithm. So what we do in gradient descent algorithm, we take the derivative at a random point, and then we find the slope at the random point, we find the direction toward a point that the function is decreasing. And then we update the current estimate for the parameters equal the previous one minus the derivative times a learning rate or a step. So when you compute the for a point, compute the partial derivative with respect to one parameter at one point, we wanted to see how much we need to move toward negative direction of slope. So I can take huge step, I can get small step, but there should be some rule. So we usually define a learning rate. So the alpha in here is called the learning rate. So we define a learning rate that specifies the amount, the steps or jump we are taking go toward the local minimum. So we can also consider the gradient descent algorithm as a way that let's say you are in a mountain and then you have no idea about you wanted to just go down, and then this is so dark you cannot see anything, but you have a torch, right? So what you basically do, you can see a small distance, right? So if you see a small distance that it goes down, you move toward that direction, and after you arrive there, you update, and then you look around to see which other direction you probably go more down. And then if you're at one point and then you using the torch, you see direction X is going down and you take a huge jump, then you may go at some point again climb up. But the conservative approach is to go small steps to make sure that you are going down, and then if you arrive at some point that this is increasing, then you can go back and or modify your direction. Note that in real situation this is not we don't have one parameter, there are millions of parameters. In today's neural networks, the number of parameters are easily 100,000 for a classifier, for a very decent classifier. So another way of showing the gradient descent, usually in 2D, we have these contours. Let's say these are the contours, and this is correspond to the minimum. So what we do basically, we start at a initial random point, and then we move toward the opposite of the growing slope, and then we go here, and then we go here. So what will happen if the learning rate is large, then you may jump over a local minimum. Let's say if I'm here, if I am at this point in this curve, and then if the learning rate, the next step I wanted to go, next jump I want to do is high, then may I jump here. Okay, so I just basically skip one local minimum, right? So the step should be small. But the problem with the small steps is also is that your algorithm is very slow, might be very slow. So fortunately, there are techniques like they have an adaptive method of specifying the learning rate. In fact, one of the hottest topic, during 2010 until 2015 and 16 was how to find an adaptive learning rate for the gradient descent algorithm, and there are now very powerful techniques like AdaGrad and also Adam Optimizer. They will consider these to have an adaptive learning rate. But for now, we assume that This is a user defined, you specify the learning rate. Another practice is when you are starting doing the iteration, we start by big jumps. As we proceed, we decrease the learning rate. So this is how the gradient descent algorithm works. So you should know that this is a partial derivative. This term is a partial derivative of the loss function with respect to the in here the kth parameter, and at iteration t. So what we do, the update at the time t plus 1 is the previous estimate for the parameter k minus, this minus is because we wanted to move toward the negative direction of slope, and then this value is the magnitude of the slope. So this basically this notation means you take the derivative with respect to the kth parameter, and then you evaluate, you compute the derivative, partial derivative with respect to this value. That means when you take the derivative, you come up with a function, and then you plug into function the estimate for the current estimate for the parameter. So this one, don't get confused. This line means that you compute the derivative, and then you compute the derivative, and then you plug in the value current estimate for the parameters to find the slope. That basically that gives you the magnitude of the slope. This slope is high or low, and how the next jump should look like. Okay, so this is the gradient descent algorithm. This is well defined in scientific libraries, and they are very powerful methods and optimizers based on the gradient descent algorithm. You can use those functions when you wanted to do the optimization in order to find the parameters for the loss function. So one of the problem with the gradient descent algorithm is it could be very slow. The reason is when you're forming the objective function, we are computing the loss function. We are computing the loss or error or objective function over all samples, which is n, and n at some point could be an order of like 10 millions or more. 10 millions or more. That means for if imagine you have also p, you have 80,000 parameters. So for each parameter, and then you also do, let's say, 1,000 iterations. You say 1,000 iteration. And then for each parameter, you need to do 1,000 iteration, and also do the sum over 10 million, to do this sum over 10 million. And it could be very slow, and then the entire iteration you are doing is then 1,000 times 80, 1,000 for 80 parameters times 10 million. You see, this is a very big number in terms of the complexity. Then in order to reduce the computational time, there is a technique called stochastic gradient descent. So for the stochastic gradient descent, what we first do, we define the error or loss function for each sample. So we can say that the total error or loss is a sum of the small errors for each sample for the current parameters, and then we define the j superscript small j. This j means sample jth is equal to y jth, the output, and then function for the input jth. So we define this one, and then the stochastic gradient descent algorithm is very similar to gradient descent algorithm, but instead of doing the sum over all samples and computed the loss function, it only considered the loss function for one sample. So algorithm then evolves as follows. So like the gradient descent, we start from a random point, and then while the maximum number of iterations reach, or the we don't see any improvement in the parameters, we do this iteration for each sample, and then we run a loop for all parameters. In here we have p parameters, and then we basically update the weights based on or the parameters based on the taking the derivative with respect only to one sample. So the loss function now is a function of basically the difference between the actual value and estimated value for one sample. So we don't need at this point to do the sum over all samples like the complete loss function. So it basically says, okay, find an estimate for parameters, take the derivative for the current sample. This current sample basically hopefully led us to go toward the local minimum. In fact, you may argue that so it only optimizes the parameters with respect to one sample and may not let us to go to the local minimum, and this is a true objection. And in fact, sometimes the stochastic gradient descent takes a lot of time to converge. So you may at some point, let's say, if for this curvature, if you are doing the stochastic gradient descent algorithm, you may do different jumps. You go here and then go here, go here, go here, go here, go here, go here, and then, but hopefully at the end you go to the local minimum. But practice has shown for different examples this is a very powerful technique, and it's computationally much more manageable, because now you can use the distributed models and system in order to run the gradient descent algorithm. Note that for this case, you can just divide your data to different batches and then run the gradient descent algorithm on different batches until it converges, and then run it on different machines. So this is called the stochastic gradient descent. So basically we take the jump based on the new loss function, which is defined only for one sample at a time, and then but iterate over all samples. So as I said, there have been lots of research, and there are other optimizers available these days, usually for big data and for real applications. When you have tens of to 100,000 parameters, they use a stochastic gradient descent. They also use other optimizers. The most popular one are adaptive gradient algorithm. Is called AdaGrad, or also root mean square propagation, RMS prop, and also the one that combine these two is called the ADAM, adaptive momentum estimation. Is a very powerful and simple and computationally effective technique to do the optimization and find the parameters of the loss function. So there's some very recent study. They show that for some practical examples, stochastic gradient descent outperforms ADAM. But when you're using TensorFlow or other deep learning libraries in order to do the optimization, you can try different optimizers. Basically, that's as there's an input argument, then you can set it to be ADAM, you can be the stochastic gradient descent, or whatever techniques is implemented in that scientific library. Today's libraries, they all contain all these three methods, and in addition to gradient descent and stochastic gradient descent algorithm. But the idea behind them is very simple, based on the derivative and iterative. And then what we need to know that all these techniques only find the local minimum, not global minimum. So the techniques that they're using to find the global minimum is to set the algorithm for different random initial points. So basically we have a random initial points. If we repeat the algorithms with different random initial points, hopefully one of them will let us to go toward the true global minimum. So for instance, if you have a curve like this, so if you start by different random initialization, let's say start from here, and start from here, this one probably will take us to this local minimum, this one will take us to the global minimum, and this one take us to this local minimum. So if you do the random initialization and repeat it a couple of times, we hope that for one case it will go to the local minimum. Another way is we are not taking care of that much about finding the local minimum. We are looking at the output. If the output is desirable, then that means the optimizer is doing their task correctly. So let's say we are using a classifier in order to do the speech recognition, right? The speech recognition, just the input is voice and output is transcript saying that what we basically utter. So if we compute the output and compare it with the actual transcripts or labels, if they look good, if the accuracy is 90%, if the confusion matrix looks good, then we are done. We don't care about okay, we got to the local minimum or global minimum or whatsoever, and that doesn't matter. So as I said, today's most of the state-of-the-art classifiers for big data are based on neural networks, a different version of neural networks, feed-forward neural network, or recurrent neural networks, or self-organized map neural network, or convolutional neural networks. All of them, they use this optimization technique, which is based on the gradient descent or one of their extension, in order to find the parameter. So basically the training part is to find these methods. This is a very brief introduction to gradient descent algorithm. In the next step, in the next video, I'll talk about the neural networks, and then there we'll use another loss function which is called the cross entropy in order to find the parameters of a neural network. I wish you all a good day or night, and I'll see you in next video.